I'm going to talk to you about how we are actually using software to create mechanical linkages between completely different materials. So as we know, in traditional manufacturing, we have an assembly line where multiple different parts come together and we fasten them together to create an end-use product. But manufacturing is going digital, and the real end-use goal there is to have a completely digital manufacturing cell that can accept raw materials in a digital file and output an end-use product. Additive manufacturing will likely be the solution to how we enable that. But the truth is, in 2017, additive is mostly limited to printing single materials. Some materials can be printed together, but that's a very small subset of the engineering materials in the world. This is a very big problem. Some materials, as we know, are like oil and water, and they just don't stick at all. Others will delaminate over time. And so we could solve that with fasteners, but that's a pretty expensive solution, and it doesn't lend itself particularly well to digital manufacturing environments. So to solve this, we created a technology called Mosaic Rivet. And what we're doing is effectively accomplishing the same goal as a bolt, but using a digitally defined rivet. A base material can be additively manufactured with receptacles in it that a second material is bulk deposited into to form a mechanical linkage, and then the second material is printed on there. So those two materials are interwoven together. Again, we're accomplishing the same function of a bolt, but this is a completely digital implementation. The mechanics are pretty simple to visualize, but I want to show you how this is incorporated into software, because that's really where the magic happens. This is a CAD model of a shoe, which would be 3D printable, except for the fact that the materials that comprise it don't stick together. And so we can use Rivet to solve that problem. The CAD data is pulled into Rivet software, and the first thing it does is identifies that interface between the different materials. It then identifies Rivet locations and optimizes them for performance, modifies the surface geometry to create the receptacles, and then creates toolpath instructions for a digital manufacturing system to execute to create that multi-material part. And by doing so, we have a fully automated multi-material end-use product created in a fully digital way, no manual labor required, and no external fasteners required. There are kind of three buckets where we see this applying, three different areas. The first being the polymer space. So using different materials together that traditionally just wouldn't stick and wouldn't be able to be printed together. So you could think about thermoplastic elastomers with rigid engineering materials like nylon in order to make integrated assemblies and even grip fingertips for a prosthetic hand. We can think about interfacing additive with metal in applications like the construction of a smartphone casing. And then the one that excites me the most is the hybrid, where we use additive manufacturing and interface it with traditional manufacturing. That's how additive will really make its way into manufacturing. So for instance, if you want a printed circuit board to be interfaced with additive, we could use Rivet for that. And even using additive with traditional natural materials like wood, using subtractive manufacturing, we can create receptacles in wood, and we've shown that we can then interface additive with wood. If you think about all of the applications that fall into these buckets, where an engineer in the past would have said, it just can't be done. These materials don't stick together. It's really exciting to think about this unexplored problem space. And speaking of applications, there are a couple industries who have been particularly progressive in terms of implementing digital manufacturing technology. In the shoe space, there's a drive to make a fully customizable shoe that's printed digitally. And we're almost there, but one of the big challenges is making the entire shoe. And we are working with some partners to use Rivet to solve that problem. And another one is the traditional automotive space, where the name of the game is, of course, reducing part count and simplifying assembly. By making integrated assemblies that are additively manufactured and multi-material assemblies, we can reduce the number of parts that go together, no fasteners required, and of course make really simple but complex assemblies. A couple examples being integrating suspension into a chassis, as well as integrating seating into a chassis. So I've shown you how we can create the effective bolts, but using a digitally defined rivet. And I think the lesson there is that sometimes the problem of yesterday doesn't fit very well. Sometimes the solution of yesterday doesn't apply to the problem of tomorrow, even for something as ubiquitous as a nut and a bolt. I'm Mitch Debra with Mosaic Manufacturing. Thank you very much.